Great, thanks, Blakesley, and thanks everyone. It's great to be here. I'll be telling you about white dwarf supernovae, and I'll explain why I use the title white dwarf supernovae as opposed to just type 1a supernovae in the talk. And then both from the side of astrophysics, like learning about these objects, and then also from the cosmological applications. So in fact, this is a review. So I was here on sabbatical basically a year ago is when I started on sabbatical for a semester. And one of the things I did during that sabbatical was write this review article on the observational properties of thermonuclear supernovae. And in writing this review, it was really nice because it just reminded me how vibrant a field this was. We got instructions for the review to limit the review to 50 references. And there were 3 authors. And we basically each used up 50 references. And then in the end, when we got together to look at our sections, we added 50 more. So we ended up with 200 references. And the editor was like, OK. And we consciously made a decision that we would only reference papers in the last few years. So really the bulk of the papers that we referenced here were 2010 and later. So it really is a vibrant field. It's kind of nice to work on it. So I'll be pointing out some highlights. One thing is this was a review on observational properties, and really there's a whole bunch of theoretical development that's also been going on for quite a while. I won't touch too much on that, unfortunately, in this talk. Okay, well, I'll start with maybe a sort of theory slide, but that will be basically it. So just as a reminder about supernovae, and you're probably familiar with these 2 different kinds of supernovae, but just a word on the energetics. So the normal kind of supernova that we kind of think of a massive star blowing up at the end of its life, we would call that either a core collapse supernova, meaning the explosion mechanism. It's really gravity that's providing the energy, the collapse of this core down to either a neutron star or a black hole. And the progenitor is a massive star. So either you could call these core collapse supernovae or massive star supernovae. And the energetics there is basically you have this iron core, which is roughly the size of a white dwarf. It collapses down to the size of a neutron star, and it liberates about 10 to the 53 ergs of energy in that process. Most of that is the neutrinos. And so we don't easily detect them, though of course we did detect them in this one case for 1987A. About 1% of the energy goes into the kinetic energy of the ejecta. And that is much bigger than the binding energy of the envelope, so it easily removes the envelope and blows up the star. And then 1% of that, about 10 to the 49 ergs, are radiated as photons. So the kinetic energy of the ejecta thermalizes the envelope, and you get the light out that you see. For type 1a supernovae or for white dwarf supernovae, it's a bit different. So these we call the explosion mechanism so we call them thermonuclear supernovae because the energetics are driven by thermonuclear fusion. The progenitor, so thermonuclear is kind of the analog to core collapse. And then these are also called white dwarf supernovae, which is the name I like, where this is the analog of what the progenitor here is. So these are exploding white dwarfs. And so for simplicity, if you take a Chandrasekhar mass white dwarf, here's the radius. The binding energy is only about 10 to the 50 ergs. If you calculate the fusion release going from carbon and oxygen to iron group elements, you get about 10 to the 51 ergs. And the main element that you produce that has one of the most abundant things that you produce in this fusion is nickel 56. Okay? So carbon and oxygen both have equal numbers of protons and neutrons. All the fusion here are strong reactions that happen quickly, and so you have to have equal numbers of protons and neutrons in whatever you form promptly in the explosion. And so that's why nickel 56 is one of the most tightly bound nuclei in the iron group, but with equal numbers, 28 protons, 28 neutrons. Okay. So the kinetic energy release there, that's 10 to the 51 ergs. That energy, it's just coincidentally the same as the core collapse. You can see that this is really 100 times more powerful, but in terms of what we see, they're quite comparable. Most of that fusion energy actually goes into expanding the star. Okay? In fact, almost all of it goes into expanding the star. And if that was all there was, we would not really ever see it. Because by the time the star expands to a size where we could see it, it becomes so cold that the luminosity is quite low. Okay? And so for a white dwarf supernova, exploding white dwarf, they really should be dark. But what saves us is that nickel 56, with up here somewhere, where you have equal numbers of neutrons and protons in the iron group region. Well, those elements are not stable. Okay, so nickel 58 is stable, but nickel 56 is not. And so nickel 56 will decay to cobalt 56 and then to iron 56, which is stable. And it's that radioactivity which really powers the light curve. And so it's really interesting to think that the half-life of nickel-56 is about 6 days. So if it was much shorter, like let's say it was milliseconds, then all the energy from the radioactivity would immediately get deposited into the ejecta and just be part of the expansion, and we wouldn't see it. And if the radioactive decay half-life of nickel-56 was much longer, then of course that energy would come out over a much longer timescale, and we wouldn't see it. Now, it would change nothing about nucleosynthesis or galaxies, right? Eventually, it would become iron-56 on some timescale, but our ability to see it crucially depends that it's on this sort of days timescale. So it's kind of interesting to think about. Okay, that's about it for energetics. Let's look at applications. So these supernovae, so the most common kind of these white dwarf supernovae are just normal type 1a supernovae. So these are standardizable candles in our nomenclature. You can see that if you go back, actually, I should show you. For this, the energy is processed through the envelope of the star, which could be, maybe it's 10 solar masses or 20 or 50. It can be very different. And so you would not necessarily expect the same luminosity from these objects. But here you have sort of the same amount of energy. As long as you produce roughly the same amount of nickel, you're going to get the same amount of radioactive energy out eventually. And so you might expect that the energy release for these was about the same, okay, just from a theoretical point of view. And in fact, we see that it is, in fact, about the same. There's some range in the nickel-56 that's produced in the explosions, but we can standardize that. And so when we do this empirically, we see that the luminosity is correlated with the light curve decline rate. So here on the x-axis is a measurement of that decline rate, how fast the supernova light curve declines. And what you can see is that here, the absolute magnitudes in different bands, there's this relation, which is called the Phillips relation, saying that the more luminous supernovae decline more slowly. Okay? And so there's just an empirical relation. We can use this to standardize our candle. Okay? There's more than just light curve shape. You also use the color of the supernova to add an additional standardization. Okay. The most common one that's used in the literature today is something called the SALT-2 model. And then with this kind of standardization, actually quite, it's been a couple decades now, this paper by Tripp. And what you do is you take the peak magnitude, that's here. You take some measurement of the light curve shape, that's x1, and some measurement of the supernova color, that's c, and then combine them here. Okay? And the fact that the sign of this one is different from the sign of the other one is the bane of many graduate students and professors and stuff when we get the signs wrong. You can see how it looks on the light curve. So here's some light curves. Here's a light curve fit using this model. You fit the shape of the light curve to the photometry. You measure these peak magnitudes. You measure the shape of the light curve. That gives you this x1 parameter. You measure the colors. So that gives you the c parameter. And then you apply it here. Okay. So one interesting thing about this, and it's kind of not what most people have in their minds when they think about type 1a standardization, is in the cosmological samples we use. By the way, these alpha and beta, these coefficients are basically treated the same for a whole sample. So you take a whole bunch of objects with different x1s and c's and mb's, and then you have one alpha and one beta for your sample that standardizes everything. So alpha is typically around something like 0.14 if all these things are measured in magnitudes, these three terms. Beta is about 3.1. The range that we use for cosmology for x1 and c is actually limited. We restrict x1 and c to these kinds of values. And actually, if you apply alpha times x1 or beta times c, what you see is actually the correction that you're making to the peak magnitude is actually dominated by the correction in the color. It's not dominated in the correction based on the light curve shape. And the reason is that for the cosmological samples, we kind of focus on type 1a supernovae that are up here. We don't usually use these very faint ones where you would have a bigger correction from this term. Okay? So in fact, the color is the largest correction term that we use for type 1a supernova cosmology. I'll get back to that in a little bit. Okay, so how do we know that this is true? I mean, this plot I showed you, how do we know it actually works? And this is where we have this critical sample of objects, which are type 1a supernovae in the smooth Hubble flow. Okay? So what I mean by that is sort of redshifts between, say, 0.02 and redshift of 0.1. Okay? So still quite nearby, but far enough away that peculiar velocities or any other perturbations to the expansion are negligible. So the observed redshift is basically the cosmological redshift. Okay? And in that case, then the relative distances are easy. Absolute distances, you still need to know the expansion rate. But for relative distances, the relative distance of one galaxy to another is just the ratio of the redshifts in this range. Okay? So we can see how well are we doing with type 1a supernova relative distances just by looking at our Hubble diagram in this Hubble flow regime. Okay? And it's basically independent of any other cosmological parameter. So this does not depend on H0. The H0s would cancel here. right? It doesn't depend on omega matter or omega lambda. That really only has a big effect as we go to higher and higher redshift. So this sample here is really critical, and we can test all of our models, all of our empirical calibrations in this regime. And you can see what happens. So here's the Hubble flow sample covering that redshift range. If we treated the supernovae as just standard candles, we get a pretty good Hubble diagram with a somewhat larger scatter. And then if we apply this standardization correction, we can reduce that down. The other thing important thing about this Hubble flow sample is this region is where we see all kinds of type 1a supernovae. We see the whole range of light curve shapes. We see the whole range of galaxy types, young stars making supernovae, old stars, low metallicity, high metallicity galaxies, big galaxies, small galaxies. All of them live around us in this redshift range, so we can observe supernovae of different kinds and in different environments. And that'll be important as we go on. Okay. By the way, if you have questions, feel free to interrupt, please. Okay, so let's look at some of the applications here. One, of course, is to dark energies. Of course, supernovae were used to discover the accelerating expansion of the universe in 1998. Here we are 20 years later. This is the Pantheon sample from Jan Skolnick. We have, I think, about 1,200 supernovae on this Hubble diagram. And you can, it looks great. There's lots of objects. The scatter looks good. We expect somewhat more scatter as we go farther away, and the supernovae are fainter. In fact, somehow it's easier to find supernovae far away because there's a lot of volume out there, and so you can find a lot more of them than you can nearby. But when you put all this together, here's the constraints that you get. So here are the constraints from the 98 discovery paper with just 10 high redshift supernovae in that sample, and here we are now with hundreds. So the gray is the statistical uncertainty, and the red is the statistical plus systematic uncertainty. Some people write papers saying that, are we sure that the universe is accelerating from supernovae? The answer is yes. If you want to hear more about why they say that, ask me at the end. I have some bonus slides on that. If we assume a flat lambda CDM cosmology, we can measure the equation of state for dark energy. Actually, I should have written flat WCDM, sorry. The equation of state of dark energy, and it's consistent with the cosmological constant in this sample. Okay. So the key point here is that this measurement of dark energy parameters is looking at how this curve, how this Hubble relation curves as a function of redshift. So really it's sort of a differential measurement between the Hubble flow supernovae, which anchor this diagram, and the high redshift. Okay. So again, we're making this differential measurement. Any systematics will come because there's some difference between, say, the Hubble flow supernovae and the other supernovae, or some systematic differences as a function of redshift. That would lead to a systematic here. Okay, let's look at another application, which has been quite a bit in the news lately, and that's for the Hubble constant. And so for the Hubble constant for type 1a supernovae, we need to measure absolute distances. Okay, so it's not good enough just to have relative distances like we did for dark energy. We need to know how many megaparsecs away is a particular supernova. And unfortunately, we have no direct way of measuring a type 1a supernova distance, so we have to calibrate them to something else. Okay? And the thing that we calibrate them to are Cepheids. And the Cepheids themselves, we don't have that many direct measurements of Cepheid distances, so the Cepheids are calibrated to some other geometric method that tells us how bright the Cepheids are. So that's this idea of the local distance ladder, and of course this is work that's led by Adam Rees and the SHOES team. We have these anchors, which is just from geometry, basically parallaxes or similar. Then some kind of intermediate step, which is Cepheids. I'll talk a little bit about, there's a new idea to use the tip of the red giant branch here, and then connect to supernovae, which are in the Hubble flow. Okay. This is kind of a convoluted thing. If we could measure geometrical distances directly into the Hubble flow, we wouldn't have 3 steps here. We wouldn't do it that way. In fact, there is one recent paper with using masers in the Hubble flow directly measuring the Hubble constant with geometry into the Hubble flow. Okay, but that's harder than this turns out so far. But in the future, people will just go directly to here. But the problem is we also don't have Cepheids measuring supernovae in the Hubble flow either, because the Cepheids are hard. They're not as bright as the supernovae, and so you don't see them as far out. And again, maybe in the future with bigger and bigger telescopes, we'd be able to do that. But right now, we're limited to these 3 steps. Okay, this talk I'm going to really just focus on the supernovae, and I'm not going to talk too much about the Cepheids or the geometry anchoring them, so let's just zoom in on this part of the diagram. There's supernovae in galaxies with Cepheids, and then there's supernovae in the Hubble flow. And the way that the Hubble constant measurement works is you can rewrite the equation, basically it's just the equation for luminosity distance, convert it to magnitudes, and you can write it like this, where the observed corrected, standardized magnitude of a supernova is related to this combination of parameters. So something about the absolute magnitude of the supernova, something about the Hubble constant, and then something with redshift. So this term, we can calculate for any cosmology that you want. It's really these two terms that we want to break the degeneracy between them. So if we measure one, then we can measure H naught. Okay. So the way that we've broken up the problem, it turns out, basically, in the Hubble flow region, what you're measuring is this combination, the things in parentheses. That's what you get from the Hubble flow. And you see that there are a lot of Hubble flow supernovae. You can measure this. It's just really just the mean of this very, very precisely. Okay? So the statistical uncertainty here is about 0.4% in this combination. We know that very well. Okay? But if we want to know H naught by itself, then we need to separate out the absolute magnitude of the supernova. That's what we need to calibrate. And that comes from the Cepheid observations. So those are ones where we know the absolute magnitude. We assume the Cepheid distance, so that tells us the absolute magnitude of the supernova, and that gives us this MB, and then we can break it apart from the H naught. Okay? So here's where you have more of the uncertainty. The statistical uncertainty here is 1.2%, just because there's not that many supernovae nearby, the volume is not that big, where we can have both Cepheids and a good type 1a supernova. Okay, so that's one of the limiting factors. We're basically in the process of doubling the sample right now, but it's going to be hard to improve it much, much beyond that. It just takes time. The universe sort of produces one good type 1a supernova in this range every couple of years. You just kind of have to wait for more of them to come along. Okay, in the previous runs, there's about another 1% uncertainty in the Cepheid part, and then another about 1.3% statistical uncertainty in the anchors. Okay. And I'm going to argue, basically spend the rest of the time here, or a good fraction of the time, arguing that the systematics in this measurement, at least from the supernova side, are about 1% analysis systematics. There may be higher systematics in the lower rungs, but I'll try and argue that in the supernovae, we think it's about 1%. And so all of this together, this is basically a couple percent kind of measurement of H naught. Just as a reminder, the Planck inference, which I'll show you in just a second, is about 9% away. It's about 0.2 magnitudes away from what we measure in the local distance ladder. So that would mean that any of these plots that you see, you'd have to be off by 0.2. So this is 0.4. So the mean of all these points would have had to have been up here, or actually I think it's down here, or down here for us to get the Planck number. Okay, so it's actually a pretty wide gulf that you have to bridge if you want to fix this issue. Okay, so let me show you what that gulf is. So here it is. You've probably seen plots like this. Here is, so it's H naught. I mean, it's unbelievable to me that I'm making plots with this scale of H naught. Like when I started my PhD thesis, it was not like this. But anyway, so here's Planck measurements from the last two releases, and they're down here around 67. And then all these late universe measurements from different probes. Almost all of them involve supernovae. All of these first, however many that is, 8 or 9 involve supernovae, and then a couple which are totally independent of supernovae, just to show you. So this is from gravitational lenses from the Holy Cow team, and this is just a recent paper on the archive using masers directly in the Hubble flow so that they get a result out there. Okay. But all of these are supernovae. So this is the Reese analysis from 2016. Here are a bunch of reanalyses, including one from at the CFA by Stephen Feeney of data. And so make different choices and different analysis, and you can see that they scatter a little bit, but not very much, and certainly not enough to bring things over here. I'll talk about this paper a little bit later, and then a couple ideas. So the one thing here is that this result here from the Carnegie Chicago Hubble program does not use Cepheids. It still uses the supernovae, so it's basically the same supernovae, but the Cepheids are replaced by the tip of the red giant branch. So here, I'm not going to talk about the details of that. There was just dueling papers on the archive you may have seen from 2 days ago, going back and forth. So, but here, the point is the supernovae are the same, and the argument there is that there's something different between the Cepheids and the tip of the red giant branch. Okay? So maybe there is a systematic there that can get you to the Planck value in that part of parameter space, but that's not in the supernova part, which I'm going to focus on today. Okay, so I would argue that the supernova systematics are at the 1% level, well below this 9%. And the question, why is that? Why would you believe any measurement in astronomy to 1%, and especially one as fraught as measuring distances to things? And I want to argue to you that the Hubble constant measurement is actually a pretty easy measurement as far as these things go. And the reason is it's hard to get big systematics, because to get systematics, what you are measuring when you measure the Hubble constant is you have these calibrated type 1a supernovae with Cepheids in them, or TRGB, and then you have these Hubble flow supernovae, which are just a little bit farther away. Okay? And by really a little bit, we're talking like 25 megaparsecs to 200 megaparsecs. Okay? And so if you just do the look back time, it's still less than 1 billion years, right? It's not been that much time for the universe to change dramatically. Now, all of this is different when we talk about high redshift supernovae, but the Hubble constant measurement really is dominated by things relatively locally. Okay? The difference in magnitudes, yes, these are about 4 magnitudes fainter, but they're still 16th, 17th, 18th magnitude, places where we get a lot of signal from our objects. Okay? So the point is that as long as these two samples are the same, on whatever property you think there might be a systematic, and in fact you can construct them to be the same, then it's hard to get a big lever arm to use that systematic to push your H0 in a certain direction. Okay? And even more than that, the difference between here and here, let's say 25 megaparsecs and 200, or 80 million years and 650 million years, actually I told you that the Hubble flow sample that we use is something like from redshift 0.02 all the way out to say 0.1. You can even go farther, but then you have to include corrections for lambda and omega matter and stuff. Okay? Well, that span of the Hubble flow range is actually larger than the difference between here and the lower part of this range. And so if there were systematics, you would see that in the Hubble flow sample itself. You would see it was not following the Hubble expansion exactly as it should, because there was some systematic that was trending that line off. Okay? And so just within that Hubble flow sample, this is why I sort of emphasize how important that is, we can test for all of these systematics and then say, okay, the only way to get a systematic now in H0 is that the calibrator sample has to be systematically different than the Hubble flow sample. There are some ways that could happen. I'll talk about that. Okay? But it is hard. Okay, so let me here's a little table of sort of dominant systematics. I started listing a bunch, then I ran out of space, so there might be a couple that I missed, but I think these are kind of the main ones. And I wanted to point out that it's different whether it affects the H0 measurement or affects dark energy constraints, right? And just for the reasons I was mentioning, for the H0 measurement, it's basically a very local universe measurement. There isn't much time to play around with different kinds of galaxies or different kinds of ages for the supernovae or different masses of things or different metallicities. Okay? Whereas when you go to high redshift and you're trying to measure dark energy parameters, you have lots of leeway to change lots of things. Okay? So one of the biggest, which I won't talk too much about, is photometric calibration. It's true that the supernovae that we measure locally might be on small telescopes. In the Hubble flow, we try and use the same small telescopes, but there are a whole bunch of small telescopes. You're not sure that they're all calibrated consistently. At high redshift, we have to use bigger telescopes. Then you worry that those are not calibrated with the small telescopes perfectly. So this is a problem, and this will continue to be a problem. It's certainly the dominant systematic for the high redshift cosmology. Okay? It's not the most exciting to give a talk about, though, unfortunately. I'll mention a little bit more. Okay, a lot more interesting, I think, astrophysically, are all these other systematics which are, could be from some kind of astrophysics. Okay? And I want to argue, and I'll show you some reasons, that most of these can be limited to less than 1% systematic in the Hubble flow measurement. Okay? And for example, host-galaxy correlations, I'll show you a plot in just a second. If you say that somehow the type 1a supernova knows about its environment or it reflects its environment, and so its luminosity might depend on the environment it's in, and actually we see evidence for that, could this be a systematic? And the answer is yes. But since we have this huge Hubble flow sample with hundreds of objects, and then we have a pretty limited Cepheid calibrator sample, right now only 19 objects, it's going to go up to 38, and those Cepheid objects are all in young star-forming galaxies because we selected them so that they had Cepheids, right? So then you can say, aha, that's a place where I could have a systematic. All my Cepheid hosts are all one kind, and my supernova hosts in the Hubble flow are all different kinds. I talked about that's one of the advantages of the Hubble flow. Okay? But you can then do the simple test. Let me just pick supernovae in galaxies in the Hubble flow that are like my Cepheid ones. We have hundreds of them, so it's fine if you throw away half your sample in the Hubble flow and then just look at things in star-forming spiral galaxies, just like the calibrator. Okay? And so we do exactly that kind of analysis test, and we don't see a big shift in the Hubble constant. And so you're like, okay, I want to make the most restricted cut you can. You can do that. You'll get slightly bigger statistical errors, right? Or you can say, well, I don't see any shift, so I'm going to use them all. It's up to you, and all of those lines are in some table, and you can choose whichever H0 you want, and it's not very different. Okay? So that's the advantage of being able to kind of match the calibrator and the Hubble flow host galaxies, and you can also match the supernovae to be as similar as you want. And then and see what H0 you get. And it's hard to move H0 by more than, really more than about 0.5% with this kind of stuff. All right, but we still want to test. So whenever someone comes up with some idea for some possible systematic, at least in the whole H0 measurement, we try and test that. For the dark energy measurements at high redshift, this is going to be harder because we're going to have good models of how things are changing, and we don't really have that. So I think it's going to require larger samples, like we will get from LSST, and then the high quality data that we'll get from WFIRST. Okay, so this is too busy to plot, so don't try and stare at every panel too much. But the point here is that we see actually that the supernovae do seem to know what kind of host they're in. Supernovae that are in high mass host galaxies, after you standardize them, don't standardize exactly to the same luminosity as supernovae in low mass host galaxies. And we don't know why that is. We presume that the supernova does not know what the stellar mass of its host galaxy is, but presumably this is somehow related to either age or metallicity or something that's correlated with stellar mass, and that is being reflected in the supernovae. It also could be that our models to standardize the supernovae are not perfect, and so we're not using some information that would actually make them standardize better. So it's not necessarily that the high mass host galaxy supernovae are more luminous, it's just that they don't correct to the same luminosity. So it's sort of a second order problem. Okay, but in all of these, there's some evidence you can see, stronger or weaker, that as you look at host mass, or here is specific star formation rate, various proxies for host galaxy properties, that there's something different with the supernovae, and then you can correct for this. So in fact, we do this in the cosmological analyses, using one of the kind of average size steps, like a 0.06 mag, so basically a 3% luminosity difference between supernovae and high mass hosts and low mass hosts, results in a 0.7% decrease in H0. Okay? And that's because there's really only a modest difference between the average host mass of the calibrators, which are generally more massive than the ones in the Hubble flow. And if you wanted to get rid of that, you would just pick objects in the Hubble flow that matched your host mass of the calibrators, and you could do that. All right, so hosts is kind of one thing. So how are we going about trying to test these correlations and attack them and mitigate them? So one thing that we're involved with right now is a survey led by Ryan Foley, Armin Rest, and Dan Skolnick. It's called the Foundation Supernova Survey. It's using the Pan-STARRS telescope to observe nearby supernovae, which is kind of a funny thing. The Pan-STARRS telescope, I think, has a 7 square degree or maybe 9 square degree field of view. It did a whole survey of the sky. It found a whole bunch of high redshift supernovae. And now we take it and we point it at one supernovae that we already know about, which is like one spot of this whole 7 square degrees. And the reason is to get that nearby sample on the same telescope and photometric system as the high redshift sample. Okay? And so it seems kind of wasteful, but it's very valuable data. And so we have now a few hundred supernovae that we observe this way, and we can ensure that the photometric calibration is consistent from low redshift to high redshift. My graduate student, Kyle Detman, has been working on this project. And so at Rutgers, we have a share of the SALT telescope in South Africa. And so we get spectra to confirm some of these objects and that we follow up in the past. Okay. So we released our first data release a couple years ago. Here's our 180 Hubble flow supernovae. We're basically saying, let's rebuild that critical Hubble flow sample. Before all the previous Hubble flow sample came from lots of different surveys, lots of different telescopes, let's rebuild it on one consistent photometric system. And so we think that that'll be important as we go forward. One thing I forgot to mention is the objects that we observed come from a whole bunch of surveys. There's been this rapid increase in people surveying the sky for new objects, including supernovae. And there's still amateur astronomers who do this. It's hard now to call them amateur astronomers. They're not people looking with binoculars or your backyard telescope. Like, they have essentially professional rigs that they take pictures of, and they spend every night as a hobby, like, difference imaging and looking for new things. It's amazing, and sometimes they do better than the professionals. It's really amazing. So one important thing about this is basically the whole sky now is being surveyed for these Hubble flow distance supernovae, and so we can find supernovae that we couldn't find before when people were only targeting big galaxies. Okay? So we had a bias before that all the hosts for our supernovae were in big galaxies that people happened to be looking at to look for supernovae. But now when we have these untargeted surveys, which see the whole sky, we can find supernovae in low mass host galaxies, which we often also find at high redshift, and so we want to make sure that those host samples are as similar as possible. Okay? So that's what we've done here, and I haven't plotted the host distribution, but in the Foundation Supernova Survey, we see a lot more supernovae with low mass hosts than we did in the previous Hubble flow sample. And so that's going to help us match one of these things. Okay, I want to talk about one other thing, which is, or a few other things, but one other systematic is the color. I mentioned that the color correction was the most dominant correction that we make when we standardize the supernovae. And in that formula, there was just one parameter, C, which described the color. And you could ask me, well, what wavelengths are you talking about? What phase? You know what? But the model says there's just one color parameter, and that's all there is, and we're going to correct it one way with this coefficient beta. And that's a problem that's becoming a limitation because we know there's a lot of stuff that affects the color of the supernova before it gets to our telescope. There could be intrinsic variations in the supernova explosion that, you know, it could be hotter or cooler and lead to a different color. There could be dust in many different places, so all the way from the Milky Way dust, which we need to understand even better than we do now. There can be intergalactic dust. There's a nice paper by Priest-Menard about that. Dust in the host interstellar medium, dust in the host circumstellar medium. They could all have different properties. It really does not seem to work, and now we have good evidence for it, to use one color correction parameter to standardize our supernovae is probably not what we can get away with in the future. So we've been working on trying to improve that. My student Kyle Detman has been working on looking at the intrinsic colors of the supernovae. We need to have some other intrinsic property of the supernova to compare against. And so we use the line velocity, how fast the ejecta are moving, as something that we know is intrinsic to the supernova and see how that affects the colors. In fact, fortunately, in Kyle's work, we're not seeing much of a strong effect. So it's probably something we don't have to worry about. Okay, one way to deal with this is a lot of these dust issues get mitigated if we move to longer wavelengths, to move to the near infrared. So that's one of the recent kind of developments, is that people have been moving to near infrared observations rather than optical observations of type 1a supernovae. So as I said, that's good because it mitigates dust extinction. It also turns out, and I can't explain exactly why, but it's sort of in the models, it turns out that in theory, the supernovae seem to be better standard candles when people run explosion simulations and calculate the radiative transfer. Okay, so this is a paper from Dan Kaysen showing different bands. Here's the bolometric output. This basically tracks how much nickel-56 was produced in the explosion. You can see it spans a pretty wide range. But fortuitously, in the near infrared, so in J or H band especially, you can see this version goes way down. And it's basically a conspiracy of the atomic physics to make that the flux that comes out here basically the same no matter how much total flux there is. Okay. So this is great. So if we observe here, the type 1a supernovae could be pretty good standard candles. We wouldn't have to standardize them over these ranges that you see in the other bands. Okay. The little worry here is that the near infrared, the flux that you get, the energy that's actually coming out in the near infrared, is only a few percent, maybe up to 10% of the total luminosity. And so if you're pinning all your hopes on that 10% of the flux, or you know, as I said here, like you're standardizing the tail, but there's this whole dog that you're just ignoring. Okay, so that's theory, but this is not a theoretical exercise usually, this whole enterprise of supernova cosmology. Here are some observations which show that this actually might be working. This is that same decline rate parameter I was showing before, and you can see here there's not really a clear trend in the near infrared bands. Okay? So this was a work people have known for a while, so this is over a decade old by Kevin Kershunis. And since then, people have done a lot more, collecting a lot more data in the optical and near infrared. This is gorgeous data from the Carnegie Supernova Project, paper by Chris Burns. And what you can see these slopes, these Phillips relations are pretty strong in the optical. But as you move up to the infrared, okay, they become shallower. Maybe there's a little turn at the end, but certainly in that cosmological region we're using, like they're really pretty good standard candles. Okay? And people have shown this with Hubble diagrams as well, where you get very small dispersions in the Hubble diagram, just treating the supernovae as standard candles. Okay, so in a paper with Sohail Dawan and Bruno Leibengut, we took this idea and say, well, let's try and measure the Hubble constant this way. Let's move away from using optical light curves of supernovae to only infrared light curves. And so we just fit some supernova light curves in the infrared. There's less data there, so it's a little bit harder. And we just said, okay, we're just going to treat them as perfect standard candles. We're just going to take the peak J magnitude and plot that up and see what it looks like. And surprisingly, it works really well. So here's as a function of the host type. Here's as a function of the color of the supernova, or basically the host, the extinction. Okay, we see that in the infrared, you don't have to worry about that so much. Here's as a function of the light curve shape. Okay, you can see what we saw before, that basically for the bulk of the sample down here, it's pretty flat across. The fastest declining supernovae are a bit fainter, so they're over here. But otherwise, this works really well. And so we did that. We went ahead and tried to measure the Hubble constant this way. We had our Hubble flow sample. Now these samples are smaller than the previous ones just because we don't have as many infrared measurements. We have our calibrator, calibrator sample here, Hubble flow sample here, calibrator sample here, okay? And put it all together, do exactly the same kind of analysis that you do in the SHOES project, and we get a number here of 72.7 plus or minus 2, basically 2. Okay. And then again, we tried all these different cuts, only using spiral galaxies in the Hubble flow, et cetera, et cetera. And basically, if you just look at this column of numbers, it's always in the 70s. And so our conclusion here is this is completely consistent with the SHOES results. Now, again, we were only testing the supernova part. All we did was change from supernova in the optical to supernova in the near infrared. So again, if we still used exactly the same Cepheid distances that Adam and the SHOES team used. So if there was some systematic there, that wouldn't show up in our H0. Okay? But at least from the supernova, what we can conclude is that the H0 tension does not seem to result from some wavelength-dependent effect in the supernovae. That the optical supernova-like curves and the infrared ones give you the same answer. There were a couple issues that we ran into. The spread here in the Hubble flow and the spread in the calibrators were not, this is a pretty significant difference. We're trying to explain why that might have happened. And also, the photometric calibration of the infrared is hard because the infrared bands are defined by where the atmosphere absorbs, and it might absorb more one day and less the other day. So we were running into some issues with the photometric calibration. So we think we can actually do this better. And to do this better, we have a few options. One, as Blakesley mentioned, is we can wait for W first, which is going to observe in the infrared, and we'll have great coverage over the bands that we're interested in, again, from space. And what's interesting here is on the bottom, I've plotted if you de-redshift the wavelengths to, for example, a supernova at redshift 1 or redshift of a half, what you see is, well, at redshift 1, these bands that W first is going to measure basically correspond to optical light curves. Okay? So at redshift 1 with W first, we're going to measure the same optical light curve that we measure in the Hubble flow, for instance. But there will be lots of supernovae at redshift of, say, a half that W first will observe, and those will have a lot of cosmological leverage, it turns out. That's actually a really good sweet spot to measure, for instance, lambda. And there, a lot of the flux that W first will measure will still be in the infrared. Okay? And this is a problem because we don't have that nice Hubble flow sample, a huge Hubble flow sample, to match up with what W first is going to get. And so this led some of us to propose this new project. So yeah, there's significant leverage here for near-infrared rest frame data from W first. And so we just got this approved program for this current HST cycle and the next one called SIRA, which I will explain the acronym if you want. It's in fact multilingual, but you can ask me about that. It really was cheating, and like some people really were offended. But anyway, we're going to observe, we can only get so much time, but we're going to basically double this Hubble flow sample with 24 objects which are observed with HST in the infrared. And basically we'll be on the HST system, the photometric system, which is well calibrated, and we won't have to worry about the pesky Earth's atmosphere blocking some of the light. And so there are three main goals for this program. One is we're going to actually get a spectra of the supernovae, and so we're going to get rest frame near-infrared SEDs. We'll use that as planning tools for W first, because we need to know what the SED is without the atmospheric absorption that we get for observations from the ground. We think we can get about 2.7 near-infrared only measurement of the H0. So this was the one we did before with the current ground-based data. We think we can improve that significantly. Again, it's sort of competitive with the optical, but we just don't have as many objects. So the optical is almost always going to be in the lead, just because there's just so much more data in the optical. Okay? So we're kind of trading. We have worse statistics, but we're thinking maybe we have better systematics in the infrared. We're not susceptible to all these things. And then there already was a high redshift program with HST with the same instrument, with C3IR, that did supernovae at redshift like 0.3 to 0.6. Their plan was to calibrate that against ground-based data, which they are doing, the RAISINS team. But we will be able to use our Hubble flow objects all in the same photometric system with C3IR for the whole Hubble diagram. So we can redo the dark energy measurement from the RAISINS data with this data. Okay? And we just started the survey, so we're going to do 2 objects a month that we have to trigger HST on and observe them over and over. This is kind of a funny thing with HST is the way we can do this is we don't disrupt what the telescope is pointing at, so whatever it's looking at today, that's what it's going to look at. We have to wait about 2 to 3 weeks after we tell them we want to observe the supernova before they can. Okay? And the problem is it takes about 2 to 3 weeks for the supernova to go from discovery to its peak magnitude. So basically, we have to find lots of very young supernovae, not because we want to do great science when the supernovae are young, which there is a lot of great science, but just because we have to wait 2 weeks before HST can find them. So can observe them. So we're actually right now we're intensively basically the HST, the best day to trigger is on Tuesday because they build the schedule on Wednesday and Thursday. So we want to find supernovae in the universe that were like exploded on Monday, and then we know that it's a type 1a in our redshift range, and then we can tell them on Tuesday. So it's kind of it's put a funny cadence to our week, which is basically like starting now. It's like, okay, let's start looking at the candidates. Let's have something for Tuesday. So that just started, and it's a lot of fun. We got some data already, and so we had some other fields. These fields are actually ones which were the previous Cepheid calibrators. We want to recalibrate that ground-based infrared photometry through the HST system. The supernova, unfortunately, is gone, but the stars in the field are still there, and so we can use those stars to try and do the calibration. And so, there was a type 1a supernova somewhere here in this field, supernova 2015F, and then we got the infrared images from space, and we also are going to get these spectra, as I said, with the GRISM on WIPC3IR, so we can get the spectrum of all these stars. It'll be even better when I can show this slide with the supernova spectrum in there. Okay, and I wanted to highlight my postdoc Meet Dai, who has been working on finding these young supernovae. Okay, so I have, let's see, maybe 10 minutes. I want to talk about one of the kind of big systematics that we worry about in especially the high redshift cosmology, and that's the fact that we don't know what type 1a progenitors are. Okay, and if we don't know what they are, we don't know how they might have been different early in the universe and how that might affect our measurements. Okay? And as I said, that's sort of the H0 measurement is not so susceptible to this because there's not that much time for things to change. But certainly the dark energy, the W measurements will. Okay? And when you may have heard about this, the usual way people present this issue is that are the progenitors of type 1a supernovae, is it one white dwarf that's accreting from a normal star, so-called single degenerate scenario, or are they two white dwarfs, the double degenerate scenario? Okay. I want to try and remove that notion from your mind because what we actually know is much, much less than that. What we know is probably, I mean almost surely, but probably, we don't have even direct evidence of this, that it's a carbon-oxygen white dwarf that explodes. Everything else, that they exploded the Chandrasekhar mass, that it's creating material from a companion, all of that stuff we don't actually have direct evidence for. Okay? So this question about the progenitors and our ignorance of the progenitors and the explosion is much broader than is it just single or double degenerate. It's all of these things. So what mass, what's the companion, what material is it created? Is it hydrogen, is it helium, is it something else? How does the explosion proceed? There's different ways, supersonic, subsonic. Would you expect some sort of interaction between the ejecta and the companion? And then is anything left behind? Okay, so all of those we don't know. Okay, one question is, how much does it matter? And one of my collaborators, initials AR, so I don't want to say his name and get him in trouble. Well, no, that probably tells too much. So one of my collaborators, who happens to have a Nobel Prize, asks me this question all the time: how much does it matter? He says, Saurabh, if you knew that type 1a supernovae came from double degenerate scenario, systems with this mass and this thing, how would that change any of what we do in terms of supernova cosmology? And it's actually a good question because almost everything that we do is empirically driven, so it actually wouldn't matter so much. Okay? I don't really like that answer because I want to know what the heck the thing I'm looking at actually is. So I'm interested in this question just because I want to know the physics of supernovae. But also, if we really did know that they came from double degenerate systems, then we could start to look to binary population synthesis models and see how that would change in different environments, different ages, different metallicities, et cetera. So I think there is, I think this is a good question. We should think about, how much it matters. But I think there is a good reason to want to know the answers to these questions. Okay. There was a workshop. I don't want you to read this, but there was a workshop I was helped organize in Munich a few years ago, and we got people into this, a bunch of people into a room just about this size, and we said, okay, let's make a list of all the possible progenitor and explosion mechanisms that anyone's ever thought of for type 1As, and then let's come up with arguments that that can't be the dominant source of 1As. And so in black are all the different models, and then in green or yellow or red, depending on how strong the argument was, there's an argument against all of the models. Okay, so essentially we spent the whole day ruling out all the models, and that was great. So it meant, either we have to come up with new models, or more than one model is, there's no dominant model, but they all contribute. both of those are kind of unpalatable options. And so from an observer point of view, we always want to go out and see like, okay, if this model was right, how would we see that? What are some signatures of that? And so let's go test those things. So one illustration of that I want to talk about is this really great paper led by Ken Shen, who said, well, what if, when we think about the double degenerate scenario, most people have in their mind, there are two white dwarfs, they are spiraling together, emitting gravitational waves, and then they collide, and then they blow up, okay, because now you have more than 1.4 solar masses of white dwarf material. Okay? But that's not the only way it could happen. That might happen. But another thing is that if you have two white dwarfs, one is slightly more massive than the other, well, the less massive one is puffed up. It's actually going to enter the Roche lobe of the, it's going to fill its Roche lobe as it approaches, and it's going to actually start mass transfer from one white dwarf to another, and that might be the time when the star explodes. Okay, not a direct collision, but you actually have this accretion onto the more massive white dwarf. It explodes, and then the question is, well, what happens to the other star, and what if it survives? Okay. Well, if you have two white dwarfs together, and let's say they're CO white dwarfs, that sets the radii, and that sets how close this Roche lobe would be. You have two white dwarfs together, the orbital speed is like 2,000 kilometers per second. Okay. And if the companion explodes, that means that other white dwarf is going to go shooting out at 2,000 kilometers per second. And Ken said, hey, Gaia's out there, let's wait for the Gaia data release and see if we can find white dwarfs that are speeding off at 2,000 kilometers per second. And we did. He said that maybe we could see up to 20. We found 3. So if it was 20, then we could say, yes, all type 1a supernovae definitely come from this mechanism. With 3, we don't know what to say, so that's the kind of unfortunate part. But here's a star. In fact, these are the 3 of the fastest, in fact, the 3 fastest hypervelocity stars that we know of that are unbound. Okay, so there are some stars that are moving around the galactic center faster than this, but unbound in our galaxy, these are the fastest we know of. And here's one its radial velocity is 1,200 kilometers per second. If you take the Gaia data, get the 3D velocity for these stars, they're all over, they're 2,000 up to even 3,000 kilometers per second. And these are weird stars, like, maybe like looking like they were right next to a star that exploded. In one of them is actually moving away from a place where there is a hint of a supernova remnant that's about 90,000 years old. And that is about the time that it would take at its current speed to go from there to where it is right now. So we like to say this is like fleeing the scene of the crime, like there was this explosion, the star is fleeing, and it really is the criminal. It was responsible for making the other star explode, right? It's its mass that it donated onto the other star. So this really is a fugitive star that we are tracking here. So that's kind of fun. Okay, the last thing I want to talk about is that even there's more to white dwarf supernovae than just normal type 1a supernovae. And so this is a figure from Stefan Taubenberger. We included it in our review. This is one from Eric Schau. The normal 1As that I've been talking about the whole talk are kind of like up here. Okay? And there are all these other things. We're using the same absolute magnitude and decline rate plot, but all these other things we think are white dwarf supernovae. They're just weird. Okay? And they're only a few percent, maybe up to 5 to 10% of the rate of normal type 1As. Okay? So they're not that common, but they do exist, and they're white dwarfs that explode in some other way. Okay? And the question is, what can these weirdos teach us? Can they teach us anything about the normal ones? Why does nature make some like this and make most of them normal? And so one that we've, in our group at Rutgers, has been really intensively studying are something called type 1ax supernovae. And one of the, I won't even go into the details about all, what makes what, but one of the great things about this is the only white dwarf supernova system where we have a detection of emission before the explosion. Okay, so at the location of the supernova. So here is the host galaxy of that supernova. The supernova went off in 2012Z. And here's some images in 2013, so that show the supernova. And then at that position, if we go back to earlier data that just fortuitously existed in the Hubble archive, there is something there. It doesn't look like much, but it is a smudge that I've grown to love. There is a star there, and you can measure its properties. And it's blue, and what we think we're seeing is a helium star, so a star where the hydrogen envelope has been lost, that is the binary companion of the white dwarf that exploded. And so this was donating helium to the white dwarf that exploded. Okay? And in fact, we have other evidence, and this is work with my graduate student, Isa Camacho-Neves. I saw Viraj Pandya walking around earlier. He helped write some of this pipeline. Anyway, we have some evidence that in these explosions, the white dwarf does not completely disrupt. you remember all the way back to my energetic slide, I said that you get 10 to the 51 ergs of energy in the fusion. The binding energy of the white dwarf was just 10 to the 50th. That's not that far apart. You can imagine a weak explosion would not unbind the star. And so that's what we think is happening. And so we have a whole model for how this could be, and some kind of words about what's going on. The really surprising thing is that we might understand these weirdos better than we understand the normal ones, because we have a lot more clues on these weirdos, like it can only come from this kind of system. We have a progenitor detection. The explosion is kind of weird. We see evidence in the spectra for various things, like this bound remnant, this thing left behind. We don't have all that information for the normal ones, but we might understand these weirdos better than the normal ones. And then the question is, okay, if we understand these, what does that tell us about the normal ones? Is it telling us anything, or just sometimes nature is weird?
Do you see the helium star again now?
Yes, in fact. So we've been following it, and the light curve has plateaued, and so yeah, it's still there. Okay. It's actually about twice as bright as it was before, and we don't know why. So it's interesting. Expect a paper by Curtis McCulley, who I've been emailing every week to get that paper out. Okay, that's it for me. So just basic conclusions. I just wanted to argue that type 1a supernovae are really excellent extragalactic distance indicators. And in the H-naught application, it's really hard to get big systematics because it's always a differential measurement, and you can make those samples as similar as you want. Right? The Cepheid ones, you're basically limited with the ones you have, but the Hubble flow sample you can really tune to match the Cepheid ones. And so we think the H-naught systematics from the supernovae themselves are only about 1%. Systematics are a much bigger deal for dark energy, where you go to higher redshift and the samples and populations might be different, and our lack of knowledge of what the supernovae are might be more significant. Okay? And so it might require great increases in data quantity with the Rubin Observatory, and then also data quality with WFIRST to really get at the dark energy questions. All right, that's it for me. Thanks.
So how many more cases there could be of archival data containing basically the progenitor?
Yeah.
Are people actively searching?
Yeah, absolutely. Yeah. So every time a nearby supernova goes off, people look on the archive and see if they're. And it's great. It's like I don't know if it's exponential, but it's like as HST collects more data, then there's more data for there to be. So it's really great. In fact, the one that we saw, the reason HST observed it, it happened to host a normal Type 1a supernova in 2002. And Adam Rees's project was getting Cepheids in that galaxy. So it had 60 orbits of very, very deep imaging to get the Cepheids, and that helped us find the supernova. So it's actually rare to find that deep imaging of a galaxy, so that's not going to happen that often. But now many nearby galaxies have been observed with HST, and I encourage you, if you're interested in nearby galaxies, observe more of them just for us, so we can have them in the archive and we can look later.
I was just going to be your plant in the audience to ask about your bonus slides related to H-naught.
Sure, yes. Okay. Overtime. All right. This is about whether the universe is accelerating. Yeah, so, well, okay, so let me, yeah, okay, so, all right, let me do this one. It's the same, well, this is being recorded, so I should be a little bit careful. But anyway, so there are people who've looked very hard at the supernova part and said, maybe the supernovae are not as good standard candles as we think. And there are a few things that people argued. Most of them, it's just not having dealt with the data enough to know all the details of it, and that's usually explains it. So one of them was this paper, which the Charles Nielsen et al., which argued, it was this kind of strange argument, which said that if they did a certain different kind of analysis on the data, they got error contours in omega matter, omega lambda, like here, and that their 3 sigma contour was consistent with the no acceleration. Okay? And that's just from supernovae. And it turns out there was sort of a particle physics person leading this, and they said, well, the gold standard is 5 sigma, and so, this is not, the supernovae are not evidence for acceleration. How dare a Nobel Prize have been awarded for this and so on. So first of all, the analysis that they did was too simplistic. It didn't include the covariances that we normally do. And so this paper by Rubin and Hayden showed that if you do things that, the way we kind of normally do it, you get something like this. So it really is beyond this 3 sigma. But it's true, either way, it's not beyond 5 sigma. There's some region down here which is, still allowed at 5 sigma. And to me, the big issue is that's assuming, they ignore all the rest that we know about the universe, right? That really requires a very low omega matter as well, right? So, and it's certainly far from the flat line. So if you exclude the CMB exclude just counting how much stuff there is that tells you that omega matter is close to 0.3. If you allow any of that back in, then it's many sigma this detection of acceleration. So they've also so this has led to some issues with peculiar velocities and big flows that could affect the H naught and stuff. So I think it's been hard to keep track of the back and forth. But one of the interesting things is in GR, it's not clear how to deal with. So GR is nonlinear. So we have this idea that everything should look like the Friedman-Robinson-Walker metric on average on large scales. But it's not clear that you can just go to large scales and get the average the same because it's not linear. So that really is underlying a lot of the criticisms here, that maybe we just have the wrong model of cosmology. And that's like way out of my
I have a question.
Sure.
I'm wondering, with W first and LSST, there's going to be increase in quality and quantity, and that's basically going to be just driving the error bars down. Would you say that's a true statement, or do you think there'll be maybe some more surprises?
Do you mean like more surprises like that we would find a non? Yeah, I mean,
Like
the whole goal.
could shift in some way
Yeah.
unexpected, or
Yeah. Again, for H naught it would be hard, and it's actually hard to see where LSST and W first will really add to the H naught because it is again so local. For the dark energy things could shift a bit more, just because with those new missions we'll be on a better photometric system for all the data, and so maybe if there's a systematic like that, things might shift. I think what it also will help us is that it's not just beating down the error bars, it's getting enough data to learn about systematics, and maybe systematics that we don't know about yet. We have 1,000 objects, but when you have 100,000 or 1 million to play with, then you can really test for more subtle systematics. You can say, well, let me just look in this part of the sky, let me just look in that part of the sky. Do I get the same cosmology, or do I not, and stuff like that. So I think it will help us both, reduce the error bars, but it'll let us be also more confident that the systematics are not, much beyond what we think. Yeah.
Go ahead. You said you sort of had this energetics argument where you said it's not clear if the white dwarf just necessarily disrupts or not. It survives. If it survives, would you expect a repeat supernova?
That's a great question. So in fact, Ken Chen, who I mentioned, and Tony Pyro and a couple other people, they have this paper draft, which I've told them to publish, called recurrent supernovae. So a supernova is supposed to be the terminal stage, and you're not supposed to have anything beyond the supernova. But in fact, in this case, where if that companion star did not get flung out of the system if you have a weak explosion, which could happen, and then it was still accreting, you could imagine that you get multiple of these weirdo explosions in that case. Yeah. So to me, I want people to write papers about what is left over. Is it still a white dwarf anymore? Has the degeneracy been lifted? Is it something else? So there is some papers by Josiah Schwab and Ken Chen on this. Basically, it turns out enough nickel-56 pollutes that star that it becomes like a radioactively powered star for a while. So it's a lot of cool stuff to look at. And we'd love to be able to see that in the observations.
So sort of perhaps related to that helium white dwarf that is now brighter than it was before.
Yeah.
You want to speculate about?
Yeah. So we don't think it's actually a helium white dwarf. We think it's a helium star, meaning so like it was just a normal star. We think maybe it's something like 7 solar masses, or I forget that was the 4 solar mass star. Let me actually go to the model so I can show it to you. Yeah, so here is here's the starting situation. You have 7 solar mass star and the 4 solar mass star in close binding. The 7 becomes a 1 solar mass white dwarf. This 4 solar mass, there's mass transfer back and forth. For a short period of time, it becomes like 11 solar, and it gets almost all the mass gets dumped onto this one. It evolves like a more massive star then, and so then it has this helium core where it's already fused to helium, and then the hydrogen is removed from the binary orbit, presumably. And so that's what you have in 2 phases of common envelope evolution. And then you're left with just the helium core, which may be helium burning in its center, but it's helium on the surface, and with the white dwarf, and then it's transferring helium. So that's the scenario here. And then so we would expect if this exploded and it was detached, then this free-floating helium star should be out there that we could try and look
in that sense, there's no reason why it should have the same brightness as before.
Right. So yeah. So there are lots of reasons why it could have been hit with a bunch of supernova ejecta and some energy been put into it. So yes, there are reasons why it could be brighter. So if it was fainter, we thought we would have a problem. If it went away, for example, then this model really wouldn't work. But it is still there. We're just trying to explain where did the extra energy come from and what will happen to it over time. Yeah.
All right, if there's no more questions, let's thank Saurabh.